About LEDs. LEDs and LED lighting, as we all know, we've all used them, just a simple dropper and an LED to get lighting. Makes a big difference to the look and the ambience of a layout. As you can see behind me, or I particularly like in this one, the more subdued lighting on the outside and the more stark fluorescent lighting inside the factory. How they got the ambience to illuminate inside a building. And we might skip over the ambience that's implied in that. So we're looking at LEDs. And we'll start off by looking at their characteristics. Firstly, they're cheap compared to filament incandescent types. Even with all the price increases we've had recently in electronic components, I went into eBay, as you can see there, I could get a bundle for £2, but roughly tuppence each. So they're very cheap to use, and I have to replace them, very cheap. They also have a long life. Lots of manufacturers quote 20,000 hours, 50,000 hours of continuous use without any noticeable degradation in performance. That's as opposed to P bulbs and so on, filament types, which have a lifespan of something like maybe 2,000 hours. So they're cheap and long lasting. They also have very low current requirements compared to filament type bulbs. I've quoted 3 milliamps up there, but you can, as you'll see later, we can get them working satisfactorily, sometimes right down to microamps. So they're very low current. They put little strain on your power supply. Because they have a very low current, they don't heat up. It's not like they heat an element that you get inside a filament bulb. So they stay cool, unless, of course, you go for the powerful LEDs, the types you get to illuminate your back garden and so on, which are high power and are mounted on aluminium bodies to dissipate the heat. But from a model railway point of view, we're looking at low current and cool to the touch. They're also handy for any need for flickering or flashing and so on. You can switch off and on a LED as many times as you like, and it doesn't impact on its general lifespan. Unlike filament bulbs, where rapid switching is not good for the element. So if we want twinklers, we want flashing lights and so on, they're ideal for that. And they come in all kinds of colors and shapes and constructions. Some are surface mount, some are 3mm, some are high intensity, but we'll look at that slightly later. So they come in a variety of constructions. There's some examples there. The standard dome shape at the top. You get ones that are triangular, which is very handy if you want to point out direction on, say, a control panel. You get them rectangular, cylindrical. The lighthouse one in particular is very handy because you can mount the main piece inside, say, a vehicle or a van or a truck or whatever, and just have a small drill hole to take the lead out to the outside world. You can get them in surface mount, you can get them in PCB mount, and different shapes and sizes. They come in 1.8mm up to 10mm. The last one, not to scale, of course, is the surface mount type. And you can get them on their own as standalone pieces, or you can get them on strips for lighting purposes, in either layout lighting or building lighting. So there's the symbol for a LED, a diode. They may be colored amber, green. Sometimes the casing is translucent, but it still has a color when it strikes. And that's a symbol in a circuit diagram. The two arrows, it's called a light emitting diode for a reason. It's a type of diode, only passes current in one direction. And the direction is of electrons is from cathode to anode. Back to that thing we discussed at the basic course of conventional current was thought to go from anode to cathode. Electron flow goes from cathode to the positive. And to differentiate between an ordinary diode and a LED, because this part here is a diode symbol, they add a couple of arrows to indicate the photons being emitted from the LED. They're available in a range of colors. I've only put a subset here. And they're obviously in the visible section of the frequency spectrum. So anything infrared and lower frequency is on one side, and UV and the higher frequency on the other side. In the middle, there's a band of visible light. It goes from red to violet, and it's measured in nanometers. They're so tiny. So people are talking about kilohertz, then megahertz, then gigahertz, and now we're up to terahertz. They're so high in frequency. And if you buy a LED, it'll be somewhere within that band for red. It'll be somewhere within that band of frequency as its main light source for orange, and so on. So they're available in a range of colors. You can also get ones that are bicolor. That symbol is two LEDs in the one case. They're in the one package, but they're back to front from each other, as you see. So if you put the power on in one polarity, one LED lights up. If you reverse the polarity, then the other light will light up. So it's not bicolor in and of itself, it's two colors within the one construction, within the one case. But very handy from a wiring point of view. You also get tricolor, as I'll demonstrate in a moment, where you've got two LEDs again in the one case. But it's different from the bicolor, because the bicolor means you can only have one color on at any one time. You've only got one polarity or the other. Here, we've got a common, and therefore we can light that LED in its own, we can light that LED in its own, or we can light both together to get a different color. So these two are distinct from standard LEDs, and also distinct is you get flasher LEDs with a little built-in flasher somewhere in the range of 1 hertz to a couple of hertz. There's some examples taken from yesterday's Rapid catalogue. There's a flashing LED, and it's flashing at 1.5 hertz. They're more expensive, of course, as you'd expect, than an ordinary LED, because they've got built-in circuitry to make it flash. There's the bicolor, again, more expensive than a standard LED. And there's the tricolor. What do they look like in practice? Here's a short video showing it. So here we can see a range of standard LEDs with the droppers. And you'll see here some surface mount LEDs on LED strips with their own built-in droppers. You maybe just see a black element there and a black one there. That's the droppers built into the strip. These are a range of colors. As you'll see, red, green, amber, blue, white, cool white, warm white, and amber. Down below, we've got the LED with the built-in flasher. On the left, we have the bicolor LED. Connected that way is red. If I reverse the connection, it's green. So the colour depends on the polarity between the pins. Here is the tricolour LED. If you press one button, it's red. Press the other, it's green. If you press them both at the same time, you get an orange hue because you've got the red and the green on at the same time. In addition to those, you have twinklers. You can get them in two kinds. You can get them, as you see, on the right-hand side. You may have got them in your house already. You know, this kind of thing here, where you use a little battery compartment, put on the light, and it flickers. You can take these apart, of course. Just take out, that's just a cover that's on it. That comes off and it'll reveal a standard LED in there. Two kinds, one kind like this, with the candle, sometimes has got a built-in little IC to make it flicker. Other kinds, like the one on the left, you can just see a little black piece here, and that's the circuitry to make it flicker. What can we use flickers for? Well, let's have a look again. Did I put this on? The one on the left has got the built-in flicker. So all it's got is the power across it. There's a dropper for it, and it flickers on its own. And that's an amber. Maybe you can't see it fully in this situation. Next to it, a yellow and a red. If you can't get the colour you want here, say you wanted a flickering red colour, you can get an ordinary red LED and put it in series with some other flickering LED. You'd have that normally, say, hidden under the baseboard, so you don't have to see it flickering. But you'll see the effects up here, red maybe for a brazier, yellow maybe for a gas lamp or whatever, or the ambers are from a local dumping its ash. They're not too expensive if you can get them, 18 pence each. If you wanted to have a flickering set of gas lights, for example, they cost you under £2 to have a whole street with flickering street lights. And then we have the surface mount components. There's your ruler. From here to here, we're just looking at 1 centimetre, so you can see how small the smallest ones are. And that's the range you can normally buy either individually, or some of the larger ones are going to be in lead strips. That's what the numbers mean. And 0402 is actually measuring it in inches. So 0402 in inches is that, but in metric is 1 mil by half a mil, tiny. Ideal for lots of applications in the smaller scales. And even the fairly larger one, the 1206, it's only about 1/8 of an inch in length. So they're very, very handy for our use. But of course, the smaller ones can be a bit of a pain to be soldering wires to, as some of us have found to our cost. So you can buy them, if you want, ready-made. They're pre-wired, they've already got droppers in them, but at a price, £2.45 each. So they're using 0603, which is not, as we saw, the smallest of them all. It's probably the second smallest of the sizes, but they're ready to go. You just put the power on and they go. Or you can get the micro-lits ones, which we have been selling for some years now, with the tiny micro-lits wire. And it's so small we can hardly tell where the wire finishes and where the LED starts. down at the bottom here. And there's much cheaper, but from China, of course. And they're using the 0402, which is the very smallest of the leads you can buy. Of course, you have to fit your own droppers in these. Let me just show you. Here's one little box I made to demonstrate before. I'm not quite in focus, I'm afraid. So I've got, you can maybe just see it here. Well, you can see it now, put it on. We've got a piece of, there's a microliths wire coming around the side, and I've just glued on the surface mount here. And it's only taken 40 microamps. Inside that switch is switching various droppers, and we'll discuss droppers in a minute. So that's at just over half a milliamp, and that's at 6 milliamps. So 6 milliamps is able to illuminate something like inside a building. But if you only want to, say, have a miner's lamp or a station master's lamp and so on, they're not meant to illuminate anything, they're meant to be viewed, like traffic lights and so on, then that's perfectly acceptable to be looked at. And tiny, tiny amounts of current, 40 microamps. And then there's this one here, which I've used to effect, which is a built-in flicker effect, and in fact is an array of different LEDs inside. Comes in the box, you take it out of the box, looks like that. It's meant to be a screw-in for the mains, but if you take this plastic cover off, then what you find inside is that. It's just a roll which you can unclip, flatten out, and instead of driving it from 250 volts, 240 volts, you can drive that quite happily from a lower voltage. And those of us who have seen our layout will probably recognize its use at the back here for the fire scene. These are not multiple LEDs. That's just the one strip at the back of that building illuminating all the windows. Right, now we know about what's available. Let's have a look at the characteristics. We'd like them all to work at 12 volts, but they don't, unless you buy ones that are pre-wired with their own droppers. You'll see here that depending on the colour, they have a different voltage at which they start to illuminate. As low as under 2 volts in some cases, up as high as nearly 4 volts in some cases. I should mention here that the current that is rated here is definitely the maximum current. It doesn't mean at all that you have to drive these at 20 milliamps to get them to light. As you saw earlier, you can drive an LED that's rated as 20 milliamps maximum to be 10 milliamps or 5 milliamps or 3 milliamps, some are even lower. How bright they go is measured in candelas, one candela being one candle, funny enough. But mostly they're measured in millicandelas, thousands of a candela, which is a bit odd because you're rated in millicandelas, which are thousands of, and then you say the brightness is measured in 10,000 millis, which is what, 10 candelas. But there you go. That's how they're rated in if you're buying them from a dealer. And the angle means this, what it says, the viewing angle. So a range of brightnesses, but also a range of voltages that get them to that point before they'll illuminate. There's some typical ones. That's a surface mount. That's a 10 mil wide, the larger size of the dome types. And that's the one I was talking about earlier that illuminates your garden shed or your outside patio or whatever. So there's an important point here, right, about LEDs. When we're looking at filament bulbs, just at ordinary incandescent bulbs, as you know, if you've got one that's rated, say, at 12 volts, it'll work at 12 volts. It'll also work at 11 volts, and 10 volts, and 9 volts, and 6 volts, just not so brightly. So you've got a range of luminescence depending on the voltage you put in. And that, I'll show that in a moment. But that's not the case when you're looking at LEDs. That's an example of one. So what happens here is you put in 0 volts, it's not going to light as you'd expect. You put in half a volt, doesn't light, 1 volt doesn't light, 1.5 volts. Then you get to, in this example, what, 1.8 volts. It just starts to illuminate. But look what happens. By the time you get to 2 volts, it's up at beyond 25 milliamps. There's only a very small window between I'm lighting and I'm now smoking. It can be destroyed very quickly. Let's have a look at that. Here we have an ordinary 12 volt filament bulb. As you can see, we can turn down the voltage appreciably. It doesn't extinguish. It just goes duller and duller and duller until we get to a point there's only a faint glimmer. So it'll work over a wide range from its 12 volt rating. Let's compare that with an LED. The LED you'll see right now is illuminated at 1.9, but has gone out at 1.4, 1.5, 1.6. There's a critical point to switch on. 1.8 is on. Anything less, it refuses to strike. But what happens if we go over voltage rather than under voltage? Let's watch for the puff of smoke. We're still within range. It's now going to illuminate. I'm going to go beyond its rating, and you'll see that the LED will change colour and then will finally burn out. Watch for the puff. Puff. Well, that means if we want to wire up LEDs, we have to know the characteristics. So here's one for an orange LED. It tells you what its frequency is in nanometers. Often get 2 different readings, by the way. One is the peak wavelength, just means what's read by a photodetector, what's the optimum figure, whereas the dominant wavelength is looking at how the human eye peaks. But for us, from our point of view, the forward voltage means that's the voltage at which you're expecting it to illuminate. And it says, we expect it to work typically at 2 volts, but don't go more than 2.5 or you're back to smoke. So it has to operate within the band of 2 to 2.5 volts for that particular orange LED. However, they're not all the same. Here's a chart that looks at various colours. There's a red, orange, green, yellow, blue, and white. And they all have different positions on the graph, as you see here. So if we don't want to go, say, more than 20 milliamps, then for the white, That means 3 volts will get you there. Whereas the blue is 2.6 or whatever. The yellow is 2.4. The red is 1.5, 1.7, something like that. They're all different. And we have to take into account when we're working out the voltage to make them work. Right, so if we want to wire a LED, we need to know 3 things. We need to know the supply voltage, which we'd assume in most cases is 12 volts. Could be 5 volts for some like PIC programs and Arduinos that drive them, but generally on a model railway, 12 volt supply, the bus is running around your layout anyway. So we know the voltage we're going to use. We can look up the chart and find out what the forward voltage is for that particular LED. And you can work out what the maximum current you want it to be. So we know the voltage, we know the forward voltage, and you can decide what the maximum current is. Obviously, if you make it 20 milliamps, you're running at the max. Not exactly recommended, but you might want it to be 10 milliamps, you might want it to be 5 milliamps. So how do we do a calculation based on that? Well, let's do a quick piece on paper here. So let's assume that we've got an LED. We know it's an LED because it's got the little arrows coming from it. We're going to put some kind of resistor here to limit the current. And let's assume for this example, it's a 12 volt supply. And let's assume that this LED, for convenience, is 3 volts to illuminate. Then we make a decision about how much current, how bright they want it to be. Let's assume we want it to be 10 milliamps. Now, we know that we want to drop 3 volts across here. That means that across here, we have to drop 9 volts. Yep. So that makes it easy because our good friend, Mr. Ohm, has got Ohm's law, which says that the resistance you need here will equal the voltage over the current. And the voltage across that is 9, and the current through it is going to be 0.01, or put another way, that's going to be ideally 900 ohms to get exactly 10 milliamps. In practice, you don't get a 900 ohm resistor. You have to go to the nearest one, which could be either 820 or it could be a 1K. And all that will happen is that the current flowing here will be slightly more than 10 milliamps or slightly under 10 milliamps. So you can do your own calculation once you know the forward voltage of that particular LED. Because you know that already here, and you've made a decision about how bright you want it. So we can do it that way. Or if you're lazy or have forgotten your Ohm's law, you can simply go on to that website that I'm showing up here. Or there's many more different calculators you can use. And you put in your own source voltage. I've put in 12 again. I've put in 3 again, but I've decided to make it 5 milliamps. And you hit the Find R button, and it tells you 1.8K. What a surprise. It's twice as much to get half the current I had earlier. So it tells you what to expect, and gives you even gives you the color code for which one to use. So that's the lazy man's method. But you have to have a dropper in order to get the correct working voltage for that LED. There's questions arise from that. What if you've got lots of LEDs? Can you put them in series? For example, if you'd 4 LEDs all struck at 2 volts, that'd be 8 volts. Can I just drop 4 volts across that? And the answer, generally speaking, is yes. Although some argue it's a bit dodgy because not all of those have got the exact same forward voltage. Even if you buy 4 red LEDs from the same manufacturer, there's no guarantee they're all exactly 2 volts, or one could be 1.9 or whatever, and you could put an undue strain on any one of them. Having said that, it's not a big issue. I'll jump over this. I'll leave it in here for folk to look at. Somebody says, what happens if I want to have different coloured LEDs in this strip? I want a red, and I want a green, and I want a blue, and I want a white, and so on, all from the same 12-volt power supply. Can I mix and match? And the answer is yes. And there's a formula you need to work out what that value would be to give you that correct match. So you'd look up all the specs for all your different coloured ones and do that calculation. To save time, I won't go through the calculation, but you get the idea. Then somebody said, well, can we put LEDs in parallel? Can we not have 2 of them in parallel and are the one dropper doing both? And especially if you've got multiple LEDs here, it's not a good idea. For the same reasons before, they're all going to be working at different forward voltages from the exact spec. You're better to have 1 each. And lastly, on the wiring, is that if you're wiring, say, from DCC, then you know that what happens is that the current reverses every half cycle. Now, it's dangerous to have a LED working with a reverse voltage, as I'll show you in a moment. So what you tend to do is put a diode across it so that in one half cycle of the DCC, it lights. On the other half cycle, it doesn't light, but that will conduct the current instead. Could be another LED if you wanted. And the same applies to AC. You're using reverse diodes. Why? Well, if you look at the spec down here, first of all, that's the spec for a LED, and it says the maximum reverse voltage should be 5 volts. Any more than 5 will draw too much reverse current and can damage it or destroy it. But if you put an LED, even the famous 1N4001s that most of us use, it's got 50 volts rating. So it can happily handle any reverse voltages that would damage that. It can handle it instead. So if you're in a situation where you think you may have transients or spikes that would destroy your LEDs, then you can put reverse diodes there to protect them. LEDs, when you light them up, you've got some control, as you saw there, depending on the voltage you put across them. But it's a bit dodgy to keep within that range between working and destroying. And you can't easily fade them. So if you want to be able to control LEDs and fade LEDs, then you use pulse width modulation. We covered that already under local control. But basically what we're doing, we're going to switch this transistor off and on at a fairly rapid rate. And depending on the width of the pulse that's coming out of here, you're going to be lighting the bulb for a short time, off for a longer time, on for a short time, off for a long time. The persistence of vision doesn't see it flashing because it's going too fast. It sees it as a dim colour. If you pulse it from here such that it's roughly half and half, you'll see it as a brighter. And if you put it on nearly all the time, it's the same as switching it on constantly, you get it brightest. So we're able to fade LEDs off and on by using pulse width modulation. Much preferable to using that with using different droppers. Then we get to diffusing LEDs. You can get some LEDs that are got a wider, more diffuse pattern. If that was meant to be, say, a lamp standard in a station, you might want to have a little pool of light. But if it's in a building, you might want it to be spreading out over the whole of the building. So you want it to have a diffuse light. And you can get wide-angled LEDs. Remember we looked at early on at the LED specs, and it covered angles. You can see one there that's got a very narrow angle, therefore you get a pool of light. That's a wide angle, so it's covering, it's still a pool, you can just see a darker bit in the middle and a lighter outer, but largely it's spread. You get top hats, you get ones that have, you can see there, have a flat edge rather than a dome. And that allows a dispersal of the LED over a wider angle for interior work in buildings and so on. And lastly, I'll look quickly at overhead illumination. There's times when you want to have LED strips to actually make your layout be illuminated rather than using ordinary house lighting. And you can buy these LED strips. They come in 12 volt generally. Sometimes they come in 5 volts, sometimes they even come in 3 volts, but most of them are 12 volt strips. And they come often in 5 meter lengths that you can cut to the length you want. And some pack in 300 LEDs in that 5 meters, and some pack in 600 LEDs. Clearly, the more closely packed the LEDs are, the less shadows you're going to get. But of course, it'll take more current. And again, you would choose your LED strip depending on the effect you want. You might want warm white. You might want bright white. You get waterproof versions, which we wouldn't normally need in a layout, but they're available at an extra price. They're all sealed. Here's what they look like close up. They come in long strips, but within each strip, you'll find 1, 2, 3 LEDs. So we're going to apply 12 volts at the end somewhere. If you cut it where you see the scissors, there and there through those little copper pads, and then we put 12 volts on these pads, positive up there, negative there, then they'll light up. And there's that little dropper resistor I showed you at the very beginning. So there's 3 LEDs in series with 1 resistor. You can have a 3 LED strip, and they come in groups of 3. You can cut it to 6, cut it to 9, you can cut it to 3 feet or 2 meters, whatever you want. And they're used a lot for even lighting within, as it says here, inside buildings and coaches and so on. And there's an example of one being used to illuminate over a layout. And the benefit is you're able to use different colors to get different effects in your layout. Using amber, say, for sunset, or bright white, or warm white, depending what time of day it is. And again, we use that in our layout here. For those who haven't seen it, on the left here, we've got a control box, which is pulse width modulating LED strips that you see at the back here. So normally we have warm white, but we can change the colors to make it amber in the evening, the sunset. We can make it blue. We can make it flash to get thunder and lightning. We've got a speaker here for thunder and lightning effects, and then the whole layout flashes bright white. So that's a look at what's available and what their characteristics are. I say, well, we're not going to cover how to mount the LEDs and what modules to use and stuff like that, but hopefully that's enough to get on with. Are there any questions?